Moving to the next topic, that is orthocentre. So orthocentre is the point of concurrency of the three altitudes of a triangle. In this triangle ABC, AD is the altitude from A on BC, BE is the altitude from B on AC, and CF is the altitude from C on AB. Now, if we join D, E, and F, that is the 4 foot of altitudes, this triangle DEF is called the pedal triangle of ABC. Pedal triangle of ABC. Now, and this point of concurrency, let's call it H, is the orthocentre. That is the point of concurrency of the altitudes. Let's talk about the position of orthocentre in an acute angle triangle. So it is an acute angle triangle, and it is quite clear from the figure that the orthocentre will lie inside this triangle. So for an acute angle triangle, H, that is orthocentre, will lie inside it. Similarly, for an obtuse angle triangle, this is an obtuse angle triangle, A, B, C. So if we drop an altitude from A on BC, then clearly this will be like this. And since orthocentre is the point of concurrency of the three altitudes, so that orthocentre will lie somewhere on this line, and hence since this altitude is quite outside this triangle, so that so the orthocentre will also lie somewhere on this line that is outside the triangle. So in case of an obtuse angle triangle, H lies outside the triangle. Let's talk about the position of orthocentre in case of a right angle triangle. We have a right angle triangle ABC with angle B being 90 degrees. Clearly AB is the altitude on BC and BC is the altitude on AB. And the third altitude, let's say BD, will clearly pass through point B. So this vertex B is basically the point of concurrency of these three altitudes. So this vertex B is the orthocentre in case of a right angle triangle. So we arrive to this result that the vertex containing the right angle is the orthocentre in case of a right angle triangle. Let's see some results related to orthocentre. So we have a triangle ABC with CF and D being the altitudes on sides AB and AC respectively. We have to prove that quadrilateral BCEF is concyclic. So what do we mean by concyclic quadrilateral? Concyclic quadrilateral, if 4 points lie on a circle, then the quadrilateral formed by joining them is said to be concyclic, and the sum of opposite angles in a concyclic quadrilateral is 180 degree. I will leave it as a homework for you to prove the same. So let's see if I could prove that BCEF is concyclic. Now see, BC subtends a right angle at F and a right angle at E. So this BC is a chord which is subtending 90 degree at F and E. So this BC must be some diameter of some circle with F and E being some circumference points. So clearly BC, E and F lie on a circle. So if BC, E and F lie on a circle, then clearly BCF is concyclic. Now let's move on to second result. Is angle AFE equals angle C. And angle AEF equals angle B. Now since BCEF is concyclic, implies sum of opposite angles, that is angle BFE and angle BCE is 80 degrees. So angle C equals 180 degree. So this means angle BFE equals 180 degree and C. Also, this angle BFE and angle AFE lie on, their sum must be 180 degrees since AB is a straight line. AB is a straight line. Implies angle AFE plus angle BFE equals 180. Angle AFE equals 180 degree minus angle BFE. Angle BFE equals 180 minus angle C. Just angle C equals 180 minus angle BFE. So clearly angle C and angle AFE both equals 180 minus angle BFE. So this implies angle C equals angle AFE. Now proceeding on similar grounds, we can prove that angle B equals angle AEF. So the third result, angle ADF equals angle ADE. Basically, this angle FDE of the peta triangle DEF is bisected by this altitude. We have to prove this. So, like in previous result, we taking BC as base, we proved that angle AFE equals angle C and angle AEF equals angle B. Similarly, if we take if we take AB as the base, then this angle will be equal to angle A. And if we take AC as the base and AC DF will be the corresponding coordinate middle, then this angle will be equal to angle A. So basically what we get, angle ADF plus angle FDB equals 90 degree. Angle which implies angle ADF equals 90 degree minus angle FDB equals 90 degree minus angle A. Similarly, angle ADE will be equal to 90 degree minus angle A. So from here we can say that angle ADF equals angle AD. So we arrive to this result that the internal angle of the pedal triangle is bisected by the corresponding altitude, and the value of that internal angle FBE will be equal to 2 times 90 minus K, which is equal to 180 minus 2A. So the internal angle of the pedal triangle corresponding to angle A will be 180 minus 2A, corresponding to angle B will be 180 minus 2B, and corresponding to angle C will be 180 minus 2C. So let's move to first theorem. There are two statements in it. First one states that if H is the orthocenter of triangle ABC and AP is the circumdiameter means the diameter of the circumcircle, then PH and BC bisect each other. So here I have got the figure for right now I'll be proving the first part, and in subsequently I will be proving the second part also. So let's see the figure. This I have got a triangle ABC, and this circle is the circumcircle of this triangle. This O is the orthocenter, and this AP is the circumdiameter, and this H is the orthocenter. So we have to prove that PH and BC bisect each other. So as we can see, this BD is the altitude on side AC. So angle BDC will be 90 degree. So BD is perpendicular to AC. Then we have got this AB as the circumdiameter. So it will subtend an angle of 90 degree at any point on the circle. So this angle DCP, or which I am writing as angle C, angle DCP equals 90 degree, angle subtended by a diameter. Hence PC is perpendicular to AC. Now BD is perpendicular to AC and PC is also perpendicular to AC, which implies BD parallel to PC or BH parallel to PC. Now proceeding on similar grounds, we can prove that BH will be SC will be parallel to BP. Similarly, this CH will be parallel to BP. So both the opposite sides of this quadrilateral BCHB are parallel, hence BPCH is a parallelogram. Now BPCH being a parallelogram, hence its diagonals PH and BC will bisect each other. Let's move to the second part of this theorem. Let PH and BC this is your PH and this is BC. They are bisecting each other at A dash. So then OA dash will be perpendicular to BC and AH will be twice OA dash. So to prove that OA dash is perpendicular to BC, you could see that A dash is the midpoint of BC. A dash is midpoint of BC. Since BC is bisected at A dash, so A dash is midpoint of BC. Also, OA dash passes through O, that is circumcenter. Circumcenter O. So clearly this must be the perpendicular bisector of BC. That is OA dash perpendicular to BC. This let's name it D. AD is the altitude. Also AD is perpendicular to BC. Why? Because AD passes through the orthocenter edge, so AD must be the altitude, which implies if AD is perpendicular to BC, clearly AH is also perpendicular to BC. Now OA dash is perpendicular to BC and AH is perpendicular to BC. So if I name it as 1 and this as 2, then using 1 and 2, we can say OA dash parallel to AH. Now we will consider these two triangles POA dash and PAH, and prove that these two are similar triangles. Now in triangle POA dash and triangle PAH. Angle POA dash equals angle PAH. Since both of these are corresponding angles, OA dash is parallel to AH, so these two angles are corresponding angles, they must be equal. Similarly, angle PA dash O equals angle PHA, and this is the common angle. So clearly these two triangles are similar. So let me write it. Angle POA dash equals angle PAH. Angle PA dash O equals angles PHA. Corresponding angles. And the common angle OPA dash equals angle APH. So clearly implies triangle POA dash is similar to triangle PAH. So we just saw that triangle POA dash was similar to triangle PAH, which implies PO by PA equals OA dash by AH equals PA dash by PH. Now this PA dash by PH, this PA dash by PH, this PA dash by PH is 1 by 2, because PH is bisected at A dash, so PA dash by PH equals 1 by 2. Now if we use it also, so this implies that OA dash by AH is also equal to 1 by 2. Hence our result AH equals to OA dash is proved.